All right, folks, we are done with the first page of our notes in section 3.1. So let's jump into page 2 now. Okay, so now we're going to get into the details of how we measure linear association, and that is a word called correlation. Okay, and we should all have a general idea of what the word correlation means, but in statistics, it's an actual quantity. It's a value that can be calculated. I'll show you the formula here in a little bit. We will not rely on the formula very often. We will let our calculator do that work for us. But correlation is a very specific calculable quantity when you have a distribution of two different categorical variables. Okay, so let's start off with this question. Which set of data has a stronger linear relationship? We've got a scatter plot here, which looks to be fairly linear. I mean, look at that. That's pretty tight right there on that line. And then we have this scatter plot here, where also looks linear, but there's certainly more variability in the data. It looks like it shows, some of the points are really high above the line, some of them are fairly low. So the question is, which set of data has a stronger linear relationship? And the answer to that question is neither, folks. I was trying to trick you a little bit there. They're both the same set of data, just on a different scale. Notice the x-axis and y-axis for both are different, but that is the same set of data on a different set of axes. So that just tells us that our view of the data is really dependent on what we choose to be our x and y axes, which leads into this note I'd like to share with you right here. Choose min-max values on the horizontal and vertical axis to give you the best view of both variables. So the graph on the right I would consider to be much better. So this is a good graph because I can see the relationship between the two variables clearly. I go from a minimum value to a maximum value on the horizontal axis, and then is a minimum value and a maximum value on the vertical axis. This one over here is just plain bad. Don't do this. Make sure you choose your axes accordingly so that you get the best picture of the data. All right, so now let's talk about this thing that I mentioned is a new vocabulary word called correlation. We use the lowercase letter r to represent correlation, and correlation measures the direction and strength of a linear relationship between two quantitative variables. Now, I'm going to highlight very important words in this definition. Correlation measures the direction and strength. So every time I show you a value for the correlation R, you should get two pieces of information from that, both direction and strength. Next thing that's important, linear relationship. Correlation only applies to linear relationships. So if we see a pattern in a scatter plot that's not linear, we should not be talking about the correlation R. Last but not least, it's the correlation between two quantitative variables. And this, I'm just going to be honest with you, this is a place where you can get tricked. There might be a multiple choice question on a test that says something like, the correlation between these two variables is 0.84, and then one of the variables will be not quantitative, but will be categorical. So just be careful with that last thing there. So every piece of that highlighted definition is something that you must remember about correlation. All right, so in the picture to the right, there are several examples of what different values of correlation. In this picture, we have what just looks like a cloud of points that gives us a correlation of about 0. Here, that cloud is getting a little bit tighter, so it's now negative 0.3. The negative indicates that it has a negative association, and that 0.3 indicates the strength. Okay, so the sign of the correlation tells you the direction, and then the magnitude of the number tells you the strength. Notice this cluster is getting a little tighter than the previous one, but it's switched. It's now has a positive association, so as the explanatory variable goes up, so too does the response variable. This pattern, it's getting even tighter than the previous one. This one goes back to a negative correlation, or negative association, which is why the correlation is negative. But because the cloud is tighter along a line, the correlation will be closer to 1, negative 1. Again, cluster is getting much tighter, and then we have almost all the points lying on a straight line. You can see that's a correlation of negative 0.99. So, important notes about correlation that are all illustrated in those pictures. The first is that correlation must be between positive and negative 1. This is always true. Okay, so I can think of another multiple choice question that might haunt students. If I tell you, oh, the correlation between these two quantitative variables is 1.78, that's false, because correlation has to be between plus and minus 1. Oh, hear that, folks? The dogs are very interested in correlation. I must pause now to make sure that they have a good conceptual understanding of what correlation measures. Okay, folks, order has been restored. We should have no more issues with dogs barking. I'm pretty sure it was just a leaf that blew in front of the window, and you know that for a dog can be very, very threatening. Okay, so let's move on. As I was mentioning here, correlation is always between negative 1 and positive 1. If correlation R is greater than 0, then we have a positive association. If it's less than 0, we have a negative association. And now let's talk about quantifying strength. So correlation quantifies the strength of a linear relationship for us. And now, instead of just saying, weak, moderate, or strong, I'm going to try to put some context to that. And I'm going to go ahead and give you a graph that'll help you remember this. So I'm just going to mark on this graph a couple points here. Let's call this 0, positive 1, negative 1. And then I'm just going to put another couple approximate marks on here. Let's do negative 0.6, negative 0.3, positive 0.3, and positive 0.6. So those are just approximate marks on this line. And what we're going to do is we're going to say that if we have a correlation R of 0, we're going to say that's none. That's not a linear relationship at all. Okay, because again, correlation R only applies to linear relationships. If we have 0.3, we're going to call that weak. 0.6 we'll call moderate. And exactly 1, that's as strong as it gets, right? That's a perfect linear relationship. All of the points in the scatter plot would lie exactly on a line. And then again, same thing the other direction. We're going to call this weak. We're going to call this moderate. And we're going to call this strong. The difference between the left-hand side of this and the right-hand side of this is just the type of association you have, positive or negative. All right, so now I'm going to try to give us some idea here. This is the best I can do artistically. As we go this way, this is a sliding scale for strength, right? It's not that anything that's exactly 0.3 we call weak, and then you have to be exactly 0.6 to be called moderate. It's a variable scale. So the closer you are to positive 1, the stronger you are. Same thing in the other direction, right? So the closer you are to negative 1, the stronger your relationship is. Okay, so that's kind of a graph to help us understand that the closer we are to 0, the weaker our linear relationship is, and then the further we are from 0 towards positive or negative 1, the stronger that relationship is. Okay, so let's go and look at put some context to this correlation R. Now, by the way, sometimes R is called the correlation coefficient. I will typically refer to it just as correlation, but you may hear others refer to it as the correlation coefficient. Okay, so this example is back to the track. Here's the scatter plot of the sprint time and long jump distance data from the previous problem. The correlation for this is R equals negative 0.84. Part A of the problem asks us to interpret the value of R in context. Well, let's see. R tells us two things, direction and strength. Since R is less than 0, we have a negative association, and because the absolute value of R is close to 1, it's a strong linear relationship. And I think you can see that in the graph. Okay, you can see that in the graph. In part B, it says, what effect does the highlighted point have on the correlation? And explain. So let's go ahead, and I'm going to, here it's in red, and now I'll highlight that in yellow. It appears to me that if I were to kind of sketch what you might call a trend line in here, I might do something like this. I might sketch a line in that looks like that. Okay. And that trend line, that highlighted point appears to be furthest from the trend line from all the other ones. So here's a good explanation for the effect of that point on the correlation. The highlight point is further from the estimated trend line than the other points, so this point weakens the correlation. So this point actually moves the correlation closer to 0. And just as a little fun fact, if I were to remove that point, the correlation would get stronger. It would go from negative 0.84 to negative 0.87. All right, folks, that's it for page 2. We're going to shut this video down, and then you can pick it up with page 3 in just a moment.